Okay, so what if I told you there's a particle out there? It's kind of like a proton, but way heavier. And for 2 decades, it was a complete ghost. Today, we're going to dive into the scientific detective story of how physicists finally tracked down this heavy cousin of the proton. Particle physicists have one of the toughest jobs on the planet. I mean, think about it. They're not just looking for clues, they're trying to prove something existed when its entire lifespan is over in a flash, like a literal fraction of a second. So, how do you even begin to do that? Well, that's the heart of the mystery we're getting into today. And look, this wasn't some casual, let's see what we find kind of search. No way. For scientists at CERN and their partners all over the world, this was a targeted hunt. A mission, really. And it went on for more than 20 years, full of frustration and a lot of near misses. You know what makes this whole thing so fascinating? They weren't just stumbling around in the dark. The theory, the math, it all predicted this particle had to be real, so they knew exactly what they were looking for. But time after time, the experiments just came up empty. There were even a couple of false alarms, claims that later got debunked, which honestly just made the whole mystery even deeper. All right, it's time to give our elusive particle a name. It's called the X-ccplus, and it's described as a heavy proton-like subatomic particle. Now that phrase right there, proton-like, that is absolutely the key to understanding what this thing really is. So proton-like? What does that even mean? Well, think of it like family. Seriously, protons, as you know, are the bedrock of pretty much all the matter we see. This particle? It's a direct relative. It's the bigger, heavier cousin who's been mysteriously skipping the family reunion for the past 2 decades. Okay, so this breaks it down perfectly. Your standard proton, right? It's got a recipe. 2 up quarks and 1 down quark. Simple enough. Now, the ZXX+ uses that same basic 3-quark recipe. But, and this is the big deal, it swaps out those 2 light up quarks for 2 much, much heavier charm quarks. And that simple swap, that's what makes it the proton's heavy cousin. It's all in the ingredients. So finding this heavy cousin was never going to be easy. It needed a massive upgrade in technology. We're talking about essentially building a brand new kind of camera, one powerful enough to capture the ghost of a particle. The scene of the crime, if you will, is at the world's most famous physics lab, CERN's Large Hadron Collider. But you know what? The real hero of this story isn't the whole collider. No. It's one specific newly upgraded piece of gear, the LHCb detector. This was the tool that finally cracked the case. And I absolutely love this quote from Dr. Stefano de Capua, because it gives us the perfect way to think about this. Don't get bogged down in some abstract science experiment. Just think of a camera, a really, really advanced camera, designed to take pictures of the most fleeting events in the entire universe. And when I say advanced, I mean it. This is no ordinary camera. Forget frames per second. We're talking about a machine that takes 40 million photographs every single second. Just wrap your head around that. It's that unbelievable speed and precision that finally gave scientists a chance to spot the tiny, fleeting bit of evidence they've been chasing for so long. Okay, so let's recap the case file. You've got the motive, proving a 20-year-old theory. You've got the location, the Large Hadron Collider, and you've got the high-tech tool, that incredible LHCb detector. So now, let's get to the moment of discovery. All right, so here's the crucial part. The scientists didn't actually see the X-ccplus particle itself. I mean, it exists for such an impossibly short amount of time. Instead, here's what they did. They smashed protons together at incredible speeds. For a tiny instant, the X-ccplus is created, and then, poof, it immediately decays into 3 lighter, more stable particles. And that decay, that's the key. It leaves behind a unique signature, a set of fingerprints, that the LHCb camera was finally sensitive enough to record. So after sifting through just mountains and mountains of data, remember, 40 million pictures a second, they found it. After 2 decades of searching, there it was. And it wasn't a smudge. It wasn't a maybe. It was a clear, unmistakable signal that perfectly matched the exact fingerprints they were looking for. And get this. This wasn't some one-off fluke. They didn't just see it once. They found it 915 separate times. 915. That is the smoking gun. With that much evidence, the 20-year-long debate was finally, definitively over. The particle was real. Okay, so they found a new particle. That's super cool, for sure. But so what? What does this actually mean?
why does finding this one single elusive particle actually matter in the grand scheme of things?
Well, it's actually huge for a few reasons. First off, it confirms a major prediction of what's called the Standard Model, which is basically our best map of the subatomic world. And every time you confirm a piece of that map, the whole map gets more reliable. It also, finally, closes that frustrating 20-year debate. It proves that the massive investment in the LHCb detector paid off in a huge way. And maybe most importantly, it shows the incredible power of collaboration. We're talking over 1,000 researchers from 20 different countries all working together on this.
And what's really cool is the history here. There's this amazing historical line you can draw. The whole story of this proton family, it started over a century ago in Manchester, in the UK, when Ernest Rutherford discovered the proton. Then, in the 1950s, scientists in that same city found the first member of the Z-particle family. And now, all these years later, that same university played a key role in finding its heavy cousin. Professor Chris Parks put it perfectly. He said this discovery connects that long legacy of pure curiosity-driven research directly to the most state-of-the-art technology we have today at CERN. It's just a beautiful example of how science builds on itself, one generation standing on the shoulders of the one before. And that really brings us to the most exciting takeaway of all. For 2 decades, this particle was just an idea, a prediction on a blackboard, and now it's a confirmed real part of our universe. So it really makes you wonder, right? With these incredible new tools and so many unanswered questions still out there, what else is hiding in plain sight? What other fundamental pieces of reality are just waiting for us to finally find the right way to look?